Hey everyone, welcome to the PyTorch conference 2024. I'm Rashmi Nagpal. I'm a machine learning engineer at Patchstack, and I'm also a researcher by passion. I work at University of San Francisco under Dr. David Guy Presan, who is also present in this audience, cheering me up, and I'm so excited to see him over here. Okay, so without any further ado, let's begin. The title of the talk is Crafting Unbiased, Transparent, and Explainable Large Language Models. So first of all, let's understand the basics. What are LLMs? So LLMs are nothing but just a subset of deep learning models which are really good at understanding and generating the human language. So they are based on the transformer. It's kind of a neural network architecture being invented by Google a couple of years ago. There was one famous paper which was written by the Google researchers a couple of years ago. I think it was in 2017. That is, attention is all you need. The transformer architecture, the breakthrough lies in its scalability, which enables us to train the models on the massive data sets, giving rise to the era of large language models that we see today. The sheer size and the complexity of these neural networks, coupled with the immense data set on which they are trained on, are the key factors of the breakthrough having these kind of large language models. In fact, some of these models are trained on trillions of tokens of the data set from publicly available sources. And in essence, if I have to say, large language models are versatile language models that are pre-trained on vast amounts of text, and they are further fine-tuned or fine-tuned for specific downstream machine learning tasks. So let's delve into the concepts of the pre-training in the next slides. So imagine having a dog. So that's my Maltese breed, Fluffy. As lazy as I am, so when we bought Fluffy a couple of years ago, we want to train him for basic everyday life tasks. It could be, like just teaching him how to sit, stand, so on and so forth task. We don't want to train it for special service dog because, it's not a police dog, neither it's a guide dog or a hunting dog. So we don't want to add any kind of a special commands to it, because if you want to train any service dog or maybe like any other dog for that matter for special services, you need to train or you need to add certain specific commands to it. So that similar idea applies to the large language models while you are pre-training. Basically, we are training a large language model on a massive amount of data set to learn the patterns or relationships within the data set. So that's how the pre-training process works in the LLMs. And let's understand what are the use cases of it. So LLMs are used for a bunch of applications. One could be a reasoning, summarization, code generation, translation. Let's say you want to, translate from French to English. A lot more applications are there. Best of all, you can also prototype a lot of these applications using the LLMs within seconds, not even the months now anymore. And one of the usage of the examples I think I've given in my slides is LLMs is used for the auto completion. Since LLMs are trained on massive amount of the data set or the text, so if you're feeding the text as an input, then it is going to produce certain output. The example that I've given is the garden was full of beautiful, it could be a blank. So once you have fed that text input into the model, now the model or the LLM is going to respond with certain output, with certain probability of prediction. It could be a butterflies, or it could be, like flowers, that the garden is full of beautiful flowers or something. Similarly, there could be another example that Paris is to France, similarly Tokyo is to blank. So Tokyo is to Japan, right? So that's how the large language models behind the hoods work. They not just complete the analogies, but they also has the world knowledge that it has learned from training over subsequent, time. Now let's see one more example, and here the prompt given to the LLM is, explain me like a 5-year-old what is the quantum physics to me. And that's a very beautiful response given by the LLM is, basically it's trying to explain the superposition principle, which is giving in a 5-year-old person. So it's like quantum is like a magical ball with the two places at once. So there is a whole art of prompt design, which is about figuring out what is the text that you want to feed into the model so that the model's behavior can or response could change on the behavior that a user requires. And the approach, in which you are using a single command to get an LLM to take on a certain behavior, that's called as a zero-shot training, zero-shot learning actually. In addition, if you want to provide certain instructions so that the LLM can give you the response based on certain output or the behavior that you are expecting, then you need to provide certain examples. And that approach is called as a few-shot learning. Basically, you are prompting the model to give you the response based on certain or few cases that you have given by the user, right? Okay, so far I have briefly explained what are LLMs, what are their use cases, and how can we do some prompt design, a very high level, so that you can get the response from the LLM. I want you to take a minute. Actually, I will give like less than a minute because audience is really very less. I want you to take a minute, and just think. Think which of these faces are real one. All right. So please raise your hand if you think face A is the real one. Perfect. Please raise the hand if you think face B is the real one. Awesome. Could you please raise the hand if you think face C is the real one? I'm so excited everyone participated actually. So the response is none of these faces are real. These people do not exist on the planet Earth. I'm not sure about the extraterrestrial planets because they've never been to Andromeda or other galaxies. Okay, so this is an application of LLMs basically. So, you can synthesize the brand new data instances based on the learned patterns from the LLMs. If you are feeding in the input data set, then the LLM is going to generate patterns or data which is almost similar to what the real data looks like, right? So this is one of the examples that I wanted to highlight. Okay, so the caveat is, you should not believe in everything an LLM responds or gives you the response without even verifying. And I'll explain the statement through a couple of examples in the subsequent slides. So I used an open source image generation model, and the prompt given was CTO of a tech startup. Well, to my surprise, the output is not diverse. Quote unquote, there is a gender bias which is inherent to it. Then there is another example which is on a similar lines. It's like nurse treating the patients in the emergency room. Another example of the bias, right? Okay, so this one is different. The prompt which is given to the LLM is, Alice has N brothers and she also has M sisters. So, technically the response given by the LLM should be M plus 1, right? Because you need to include the Alice as well, right? But the response given by the LLM is M. Well, now this makes me actually question, can we really trust the large language models, especially in the complex situations or in the fields when the decision making is so critical, especially like in finance, healthcare, automobiles industry, and when also they require nuanced understanding and logical deduction? I think LLMs are probabilistic calculators for the words because they don't truly understand the concepts the way we humans understand, right? In fact, they predict the next word, like sequence of the words based on the training data on which they have been trained on. So let's get back to this question in the subsequent slides. First, I want to give this another example. This is a jailbreaking experiment in which the model was given a hypothetical question and was told to rewrite from the perspective of a character who wants to rob a bank. Now, this reminds me of a very favorite, I think Money Heist is one of the shows, yeah. Okay. So the next example is, it's very simple actually, in which LLM was told, could you please write a script for the DDoS attack? And it definitely gave a very good response to me, but with a statement of caution. That's interesting. Response given by the LLM. Okay, so next question for all of you. Now, which of the following is expected response when we prompt an LLM? So the question given to the LLM is, translate this from English to French. What is the capital of Italy? We already know the capital of Italy is Rome, right? So I'll give you actually 30 seconds and I would see how many people respond this correct. Alrighty, please raise your hand if you think the first one is the response LLM will provide. Interesting. Okay. Can you please raise your hand if you think B is the response LLM will provide? You can't be at two places at once. That's a cheat, Dr. Brazan. You have to give response to one, right? Okay. Well, let's see. Okay, so you can clearly see the response given by one of the LLMs. So this is basically an example of faithfulness hallucination. It's kind of a hallucination which arises due to the models when they are limited because of their contextual understanding, and they have the inherent noise which is present in their training data set. And therefore, the responses are not grounded in the reality. Okay, now let's circle back to one of the questions that I've raised, and I've shown the example before about the gender and the racial biases. Let's understand why this happens. That why model sometimes gives the biased, unfair responses, which doesn't make any sense. So, bunch of reasons are there, which is not an exhaustive list, but this will definitely give an overview and highlight that when the bias is there in the training data set, it's similar to saying garbage in, garbage out, right? If you are feeding in the garbage data set into the model, of course, the response is going to be trash. So the data which has been created or curated just to feed into the model, if it has sensitive features, also it could reflect some of the societal biases. So the model will learn and reproduce the same biases. There is also like the imbalance in the data set, right? When the training data set, it is like over-present or it will over-present certain perspective. And when there is a lack of contextual understanding, when the model has not understanding how the response should be. Last is the algorithmic biases. I'm not sure how many people know here word-to-vec embedding. So that's one of the NLP core model, algorithm that we use, which has been trained on Google News data set. It's a highly biased data set, and the response given by the word-to-vec embedding or word-to-vec model that we use, it's also a biased one. I'll show an example how can we mitigate the biases in the subsequent slides though. But highlight is, the data in itself, if it is biased, then model or the algorithm that we are using is definitely going to give the biased responses. There is a very famous paper, A Man is the Programmer, a Woman is the Homemaker, which basically shows the affinity of the word man is more towards a programmer than, other professions out there. Okay. So let's understand the ways how we can actually identify the biases. There is pre-processing techniques, there are post-processing and in-processing technique. So first of all, the thumb rule is the data that is being curated, it should be well representative, it should be diverse, so that from the pre-training stage in itself, we should not inculcate any kind of a biases within the model. The next is the in-training strategy, which is about how we can actually regularize the bias. Can we do the adversarial training, or maybe can we detect using the word embeddings that we are using into the model? And the last stage is post-processing. It's calibration, ROC. These are different strategies that we can use once a model has been trained. I'll show an example so that we can definitely understand what are these strategies and the techniques that we can use. Okay, so first of all, let's see the bias identification using the pre-training strategy. Okay, I Is it visible from the back? Okay. Okay, so first example that I want to present is data augmentation. There are a lot of techniques that we can use for augmenting the data if there is a class imbalance, if the target variable is higher, or maybe like there is a minority and a majority sampling of the data set. So you can use a lot of techniques, like SMART is one such example of algorithm that you can use to do the class balance. So over here, I think, just a second, I think, yeah, so the data that I'm using is the German credit data set, which has like certain features. You want to identify how many, if the person can be sanctioned a loan versus not based on certain attributes. So as you can see in here, I think once we have done the debiasing, so if you apply the SMART technique, the initial has like a different, the count of the target variable, and after applying this technique, we can see there is an equal representation. So the imbalance has been removed in this. And the second technique which I wanted to show is how we can actually debias the word embeddings. So I'm using a very small sample data, which is, like the he, she, and all of these words. And then here I am plotting and checking how we can actually debias it. So you can see clearly in the code, actually, yeah. So once that is being represented, first of all, we are identifying the vectors of the words, right? So what happens in the word2vec spaces, you have a two-dimensional, the words are being represented in a vector format. So you calculate the vectors of the words based upon whatever the the values that we have, and then we calculate their projection, and then we subtract the projection from the initial vector of the word, so that the affinity of a man, if towards the doctor as one such profession, should be less. It should be equal as a woman for a doctor, a single profession, so that both the genders have an equal affinity or equal distance from a certain specific word. It could be a nurse, could be doctor, scientist, reception, any kind of a possible, words that you can think about, which is more prevalent. And then you can do also the category with regards to the gender for, just to understand how the word, every gender, it's responding to a particular item or could be a profession. So once we did that, so you can clearly see before debiasing and after debiasing. So it's coming out to be very less. Initial was really high for a doctor and a man, and further on it decreased. And also similarly for a woman, it has increased. So that's how we can do actually the debiasing. Okay, so next one, I think, just a little. Okay, so I have my presentation here. Okay. So what are the ways in which we can, mitigate the biases? The first is definitely the fairness evaluation metrics, like the equalized odds, demographic parity, predictive parity. There are like a lot of techniques out there which will help in identifying and quantitatively measuring the biases across the different groups within the data set. The groups could be defined by us. Either the groups could be on the basis of the demographics, ethnicity, or a gender for that matter, because these are called as the sensitive or the protective attributes within the data set. right? And the next is using explainability techniques. I'll discuss in detail about what is explainability in the upcoming slides. But the basic idea is to understand why the model is performing to the way it is performing and which features are exactly there, which are weighing more importance as compared to the others. So understanding how the model is actually making predictions. Lastly, we can also introduce a couple of constraints or guidelines when we are doing the inference pipeline phase, which will help in preventing any kind of a generation of the biased content. Or we can use some guardrails during the inference to prevent the model from generating any kind of a misinformation. And that will also, it can possibly arise because of the incomplete context which has been fed into the model. So let's understand what are the techniques, how we can actually evaluate the model fairness. So there are the fairness has been classified into two main categories. One is the individual level and the other is on the group level. It's more on the granularity on the individual level and on the group level in a sense like you have the entire demographics or the entire ethnicity. Basically, it helps in identifying which model, how the model is actually performing on a holistic level or at the granular level, whether it is penalizing if the data has certain sensitive attributes versus not. So we'll understand that through an example. I'll explain that through an example. Okay. Yes. So the example over here, I'm using this German credit data set and using couple of fairness evaluation metrics, statistical parity and the counterfactual fairness. Just to explain in the layman terms what is exactly statistical parity is, you just want to make sure that everyone is treated fairly, irrespective of which group are they in. Right? Similarly, if I have to explain what is the counterfactual fairness metric, it's basically if you want to change a small single attribute in the data set, either it could be a age or a gender or any other metric within the data set that you have or any feature within the data that you have, the model's result should not be changed. So it implies that the model has been trained fairly well, right? So, okay. So this German credit data set has a bunch of features. Now what we are doing initially, because it's an imbalanced data, so we are of course using SMART technique just to make sure that minority and the majority samples are equally balanced. Then further on, we are training on the XGBoost as a baseline data, a baseline algorithm, because we want to do this kind of a loan classification, right? So this is a data set. So can a person get a credit based upon certain of the features and attributes given in the German credit data set? Once we have done that, you can see what is the accuracy of the model is coming in and also statistical parity and the counterfactual fairness, which is nothing but just a individual fairness. So statistical parity will give you the idea about the group fairness and counterfactual will give you the idea of the individual fairness. Yes, so okay. Now because this data has a lot of sensitive attributes, what I meant by sensitive attributes is sensitive information is there, right? There is also a possibility that sometimes information could have personally identified information. So that could lead to some security and privacy issues, right? Is there a way that can we mitigate that in order to build the models which are fair and not biased because of these attributes? So let's see that too. What are the techniques we actually can use to mitigate any kind of a security and privacy risk whenever we are dealing with any sensitive data sets? First is anonymization. You need to anonymize the training data set and just make sure that whatever the sensitive attribute is present in the data, either it can be removed or maybe obfuscated, right? Or maybe we can use some differential privacy algorithms. There are a bunch of techniques that we can use. Basically, what happens is we can add the noise in the data just to prevent the LLMs from memorizing any kind of a sensitive information. And finally, we can audit the model using there is also like a red team which can help in auditing the model, how the model is responding and giving a, response around it. I'll show through an example that how can we actually mitigate one of these, mitigate privacy and security risk through just one example. Okay. Here I'm using this token-based anonymization, which is one of the data anonymization technique that we can use. You can see a small sample of the data which has been on which I wanted to show that how we can actually do this token-based anonymization. So we can use also like the regex pattern that, okay, maybe the person lives in certain address, or the name of the person is this, the address, or maybe like the telephone number of the person is this. So can we create certain regex patterns so that the model will not pick up those patterns, but instead, let's say the address is there, and then you create a regex pattern which will remove that the address, and in fact will subside it with the regex pattern, so that just the basically the address, the way the address is, it should not be passed into the model. So that's how the token based anonymization has happened. Yeah. So once you have done it, so you can see how, then of course you can just fine tune or maybe just work on your downstream machine learning task. But if you see the original data, and then afterwards, once we have done the anonymization, that it has prevented the model from passing in any kind of a personal information, right? Because it is being it's being, I would say, removed all the personally identified information. And of course, I've just trained the model just to see how the model is performing with a certain loss. And there are a lot of ways we can actually optimize. It's not an optimized model, just a basic example, just to show that how we can actually do the data anonymization. And using this, I think I'm just using this pre-trained BERT model. So already like open source model. Okay. Oh, the QR code over there will give you the link of the slides as well as the implementation, the code samples. So, you can directly go through that and understand how the implementation has been done. Okay, so next one. So I think this is one of the important concepts. I think I really like this Goodhart's law, which is, can we really mitigate the biases, or is there any correlation with the Goodhart's law, which actually states when a measure becomes a target, it ceases to be a good measure, right? So this principle actually has a profound implications whenever we are designing unbiased and fair algorithms, especially in the context of unbiased and fair algorithms. Whenever we are defining, we need to understand the specific use case and the specific fairness metrics, maybe equalized odds, demographic parity, predictive parity for that matter, as an optimization targets. They might often risk the overfitting of the model to those metrics without addressing the broader principles of the fairness. If you are focusing too narrowly on one single fairness measure, then the model will not be able to achieve a good score on that metric. But it might produce some certain biased or unfair outcomes, right, in a way. I'll give through an example that what I meant by exactly how the Goodhart laws come into the picture. For example, there is a credit scoring model, right, which has been optimized for one fairness metric, let's say group fairness metric, but it may sacrifice the accuracy for all groups or lead to a higher rate of interest or false positives for one group over the another. In this case, basically it is solely relying on one fairness metric, maybe like a demographic parity as a fairness target. It can lead to distortion of the entire goal that we are working for our use case. We want the maximum accuracy. The model should be accurate, right? The fairness loss, or it should also have equal fairness towards the group as well as on an individual level. And that's where the multi-objective optimization algorithms comes into the picture. That can we use multi-objective optimization algorithm and put certain constraints in the algorithm just to ensure that whatever our goal is, either our goal is to have equal distribution across different groups, or maybe our goal is just to have equal distribution at an individual level. And at the same time, model should give not hallucinated or misinformation, but different good, accurate results. So for that, I'll show through an example. There is a particle swarm optimization algorithm that I've implemented. Yes. So it's again on the similar data, which is the German credit data that we have. And over here, you can see understanding the data, how the data is working, and then, of course, doing the class imbalance, handling the augment. So using one of the augmentation techniques just because there is a class imbalance in that particular data set. Then on top of it, there is using this particle swarm optimization and clearly stating the fact that these are the constraints. The constraints are fairness has to be higher. Fairness loss has to be lower, but the accuracy has to be higher. These are the two constraints which has been provided in here. So you can actually build a weighted summation kind of a model and play around with different constraints around it. If you can see in this entire implementation, XGBoost is definitely, like one of the baseline which has been used in the model just to compare how our model is performing with regards to the baseline. So if you do this particle swarm optimization, there is again a cost function which is associated to this algorithm. And we can always play around with, there is hyperparameter tuning we can always do with this PSO algorithm. And we can see, so you can see the accuracy of the model is actually increasing over every step, and how the cost and, the cost function, basically the cost function is defining that how our model is performing with regards to the two metrics that we wanted it to be, understanding. So that's one implementation that we can do through multi-objective perspective. Okay, so I'll just again go back to my slides. Sorry. Okay, so there is an example which I want to show in the next slide, which is about hallucinations. We see the LLMs faces a lot of hallucination kind of a problems, right? Are there any ways, can we mitigate the hallucination? That's a big question mark. So definitely there are a lot of strategies that we can use to mitigate the hallucination. But again, I feel like it's kind of an inherent nature of all of these LLMs, no matter how hard we try. Okay, so first one is through a RAG, I'll explain that how can we actually mitigate the hallucinations in the model. So we can use this knowledge augmented models in which the LLMs are basically fine-tuned to query trusted sources of the data set. Either it could be a Wikipedia data set, Reddit data set, or so on and so forth, which has been finely curated for a specific use case. Then fine-tuning with regards to this supervised learning on top of it. If you're fine-tuning any kind of a pre-trained model on any domain specific with high-quality data set, you can actually convert that to as a supervised learning, in which you are ensuring that the model is not hallucinating and it is also giving the response in that specific domain. Last one is RHLF, which is reinforcement human in the loop feedback, which is definitely like the LLMs nowadays, they are definitely incorporating this, in which you have the human feedback and the model is understanding whether the generated content makes sense versus not. Right? That will help in actually mitigating hallucinations too. One example that I was using very recently, another LLM, and I gave a question that could you give like the two resources which are based, or two research papers, right, which is based on multi-objective optimization and fairness and biases. And the response given was like pretty surprising, because if you just Google first link, the response, the title of the paper is not what the model has given it. So it's not verifiable. But personally, I feel like the hallucination is kind of a feature, not a bug per se. For sure, we can have better training data set, we can minimize it, but you can't get rid of it like all at once. Because that's what really the LLMs do, right? Even if we use any kind of a reinforcement learning kind of a method, they will definitely hallucinate. It's similar to our own nature, right? Because when we say that we know the answer, in reality, what we do is we really guess the answer. We think about it. Okay, so let's see how we can actually mitigate the hallucination through the RAG. So RAG it's kind of an AI framework which combines the LLMs with the information retrieval kind of a system to improve the accuracy and the relevance of the text that they generate. By what I meant by the relevance of the text is whatever the response you give, we are just adding some information retrieval system in the backend and trying to understand how the model is giving the response. Okay. So again, the query being given is the same as to what I've given to the LLM is, could you give the link of the 2 research papers on a specific topic? And then I'm adding documents. Documents is nothing but just kind of a small retrieval system in which it can fact check whatever the response that the model gives. So after doing that, again, there are a lot of packages in the PyTorch that we can use and understand how the model is going to give the response. So you can see the model is giving a response like towards the end. What is, first of all, here I'm also doing a sorting on the fact that, okay, what is the relevant, finding the cosine similarity between the query and the document which has been provided. Query is, I need a paper, research paper, which is from multi-objective optimization on fairness and the biases, right? So the response being given by the model along with the information, the documents which has been provided, the more similarity it is, that's how the response should be. So you can see the response that it has given is one of the papers. So that's how a small system, that's how we can actually incorporate a small RAG kind of a system into the model whenever we want to train the model or build our model towards a specific use case so that it doesn't hallucinate. Yeah, so here you can see the response that it has given and also the correct link of the paper. If you go in that link, it will definitely be the link of the paper in the multi-objective optimization. So, okay, next part. Now we were trying to understand how can we build the fair, unbiased models, right? Now it's time definitely for us to understand, how the models, they work behind the hoods. And can we actually get the explainability behind, how the model is thinking, why it is making certain predictions? There is one famous, I think, article by New York Times a couple of years ago, which is, can an algorithm really help us to send to this jail? So whenever we are using all of these LLMs, can we really trust onto them? So what are the various ways we can actually incorporate whenever we are building the large language models and ensuring that the response being given by them is making sense? To understand why a particular model is flagged for a transaction, maybe the transaction is a fraudulent, in the context of this presentation, I'm definitely including just the model explainability, that how the model is making predictions. Maybe it could be using some post-hoc analysis or troubleshooting. But again, there is also like the different levels of the explainability we can use on the data side as well on the inferencing side. So we'll just understand through the model perspective how the model is giving after making the predictions. Can we understand the response that is being given by the model through explainability? So the first example is through the Lime. It's again an open source package that we can use. Yes. So here, again, I'm using the BERT model and BERT tokenizer as well for classification. It's a sentiment classification. So what is sentiment classification is, just identifying whether it's a positive or a negative or maybe like some other categories around it. Let's say if I say, I'm really grateful to the organizers for giving me this opportunity to speak at this conference, reflects a positive sentiment, right? If I say that I don't like a certain item, then it's a negative sentiment. Maybe that movie is awful, so that reflects a negative sentiment. In a similar way, so the model was already like pre-trained BERT model, and also the tokenizer is BERT tokenizer. For sentiment classification, I'm using and adding this kind of a statement that I'm really grateful for the organizers to give me this opportunity. You can see it's a positive reflection of the positive, right? And also you can see the probabilities. on the side, that what are the prediction probabilities and which features are actually contributing in making sure that it's a positive sentiment. So in a similar way, and also it is highlighting the words which are actually contributing towards a positive sentiment. So that's one small application how we can use the Lime or one of the explainability packages to understand how the model is giving a prediction. Similarly, there is also like a SHAP tool that we can use to understand how the model is responding. Think I'll explain. There is a Captum, also a package which is available in the PyTorch that we can use to understand how the textual data or maybe like image data, it is making a prediction. And the first example is on the gradient-based attribution, which is a class of a technique which is helping in understanding the importance of feature whenever we are doing any kind of an image recognition, for instance, by just calculating the gradients of the model's output with respect to the input features that we have fed in the model. I'll explain through the implementation. Yes, so this one comes again, installing all necessary packages in the Capterm. Then I'm using this AlexNet and also like the ImageNet dataset. And a very small ResNet is the model that I'm using to do the image classification. So it will give you the predicted process, what is the image that it has been. It's a swan, it's a basically goose image. So you can see that. And also you can see which all features in the input data set are contributing and making sense. So this is one example of the gradient-based kind of an attribution. Like if you see the image, you will see the spots, which are the features or the pixels in the image, right? Which are actually contributing and how the model is giving a response and why the model is giving with certain accuracy, certain probability. So in a very granular level, through Capterm, a library, we can understand and see how the model is giving a response to a certain task, an image recognition task. There is another one I want to show. Occlusion-based attribution is also there. Basically, it's a method to understand the importance of the different parts of the input data. It could be like pixels in an image to the model's prediction. Helps in occluding. So what happens in occluding is basically kind of creating a masking on the input data and then observing how the model's predictions are making changes. Imagine that you have trained a model based on the cats and the dog, right? Now you want to understand which parts of the image are more important for the model's decision. So it will possibly occlude different parts or regions of the image, maybe like the cat's head, tail, or background altogether, and then it will see how the model's predicted image or is classified with the input original image which has been given. So if you do the occlusion on the cat's head, then it significantly change the prediction of the model. So that's what it shows. It specifies which region exactly of an image plays a huge role for the prediction of the model. You can see over here the goose head exactly, which is making much more difference, right? It's more dark pixelated. So basically it is the one which is helping or contributing, weighing more in terms of the model's prediction. The next one I want to give demo is also about this LRP, which is the layer-wise relevance propagation. I'll go through the code also. Just wanted to explain first the theory in here. So what happens in LRP is kind of, how the information is flowing through a network, through a neural network, and how different neurons are contributing to the final. Let me explain through a very basic example. Let's say you have a neural network with the 3 layers in it. First is the input, hidden layer is there, and then there is an output layer. And the output layer gives you the prediction of a class, okay? If you're using this LRP, we start by assigning the relevance score to every neuron in the output layer. And that will actually, it will propagate backwards. The more the relevance score is, it implies that feature is more correlating with the model's decision. So the propagation which is happening towards towards the input layer, back propagation which is happening towards the input layer, that there are so many relevant scores which is indicating the importance of each input feature for the final prediction that we are doing. And for sure, if you have a particular input neuron which has a high relevance score, so it will highlight that that particular feature has strongly influenced the model's final decision. Okay, so let me go on the implementation, show LRP and occlusion. So again, visualizing using again the Captain library package over here, and trying to understand here, there is a max sliding window also and the strides. These are the parameters, these are the hyperparameters in the model. So you can always play around with it and trying to understand which exactly are the features or the pixels in the image which are making sense. If you see, on the top side, the head of this goose is it's the one which is basically playing a huge role in identifying, this image belongs to a certain specific category of the animal, right? A certain category of a bird. Similarly, for the LRP, layer-wise relevance, you can see the relevance, it is basically giving certain scores around it. And then, of course, you're making certain, distribution of whatever the scores are there and plotting on the basis of those scores. So that's how the LRP is also implemented. Okay, so let me go back to the slides. Okay, so in nutshell, I think that, there are a bunch of techniques out there. There is bias mitigation algorithms, there is also like fairness algorithms, fairness metrics to evaluate the model. And there are a lot of techniques like, explainability. Can we actually integrate how our model is performing? But I feel the underlying factor comes into asking the right questions. Are we asking the right questions? Do we have the correct mindset whenever we are building the large language models? Can we understand the data that we are feeding into the model? Does it penetrate any kind of a personally identified information? Or will it give you the response based on certain sensitive attribute? Is that the model development process is super secure? I mean, for sure, there is not like 100% possibility of having a secure system, right? But there is always a nudge towards us and understanding in the backdrop that are we making the decisions and having multiple stakeholders revolve around it, just to ensure that we are not biased or we do not have the cognitive bias inculcated during the development process. And do I understand the social impact of my model inference during the inferencing pipeline? Is there a way can I visualize any kind of a biased inferences which has been propagated in the model? So there are like bunch of questions that we can ask and always brainstorm. And that's what really leads to making fair, unbiased, and explainable large language models. So towards the end, I just want to highlight that building the unbiased and fair large language models is very critical just to ensure that its benefits are being enjoyed or being widely accessible to everyone. And by ensuring that models are transparent or explainable, the model development will help in mitigating any kind of error rates are there or any kind of a biases before they can cause any big harm. I think there was one algorithm which was released like a couple of years ago in 2016. Amazon released a hiring algorithm which was again scraped off after a couple of years because it was unconsciously eliminating the women candidates because of certain features in the algorithm in itself. So that's what makes us wonder that can we ensure that the models are transparent before they can cause any kind of a harm, right? And monitoring and evaluation of our models is always vital just to ensure that who is accountable. If the Tesla or maybe like any other self-driving car is making a random decision, do we need to sue the Tesla or do we need to make a decision by ourselves, right? So there are a lot of questions that we need to ask around it and who can be held accountable for that. These are like bunch of resources that will be really helpful to understand and delve deeper into this concept of responsible AI. And I think that's all I have for you today. Thank you so much to the lovely audience out here and to Dr. Prasad for being here. And of course, to my other professors and my close friends and folks those who are here cheering me up, thank you so much. I'm highly, grateful to everyone for attending this talk. Thank you.